Yeah, good evening, everybody. I'd like to welcome you on behalf of the Faculty of Science and the Albert Einstein Center for Fundamental Physics here at Bern University. And it is my tremendous pleasure to welcome Barish from the California Institute of Technology as our 10th Einstein lecturer. Barish was born in Omaha, Nebraska, and then studied at the University for California in Berkeley and got his PhD there in the year 1962. 1 year later, he moved to Caltech, first as a research fellow, and then he became assistant, associate, and finally full professor there. And this is still his affiliation. Besides Riverside University. Barish has been involved in many very important experimental investigations. He has done experiments, for example, at Fermilab, also at the underground laboratory at the Gran Sasso, and in many other places. And what was the reason to invite him today is related to the LIGO collaboration, the Large Interferometer Gravitational Wave Observatory, for which he became the principal investigator in the year 1994 and the director in 1997. And this is really not a tabletop experiment. This is a huge collaboration which he formed involving more than 1,000 people. And so it is not just enough to have some very good scientific ideas. You also need to coordinate all this research, and you also have to make sure that the funding agencies give you the money that is necessary to engage in such an enormous enterprise. And I think Barish, with his many talents, was exactly the right person at the right time to get this LIGO project off the ground and then extend it to what is now called advanced LIGO. And it required very advanced technologies to finally detect the gravitational waves that were following from Einstein's general relativity theory already 100 years before they were finally directly discovered by LIGO in the year 2015. And Barish has played a tremendous role in making all this possible. That, of course, was recognized by different prizes. He received the Enrico Fermi Prize, the Draper Medal, the Princess of Asturia Award. And then in 2017, he shared the Physics Nobel Prize with Rainer Weiss from MIT and Kip Thorne from Caltech. So we are very glad to have him here tonight. He will also speak tomorrow at 5:15 and then again on Wednesday at 7:30 again. Everything happens here in this room. And I'm very glad to have you here and welcome you for your first lecture. Thank you very much, Barry.
Well, let me start by thanking the organizers for inviting me. I'm very happy to be here, especially in the place where Einstein was. We depend on him for all this work, as you'll see. These talks are a great luxury for me because I, for example, just came from Rome and talked to a similar broad audience, not just the physics experts, but had to do it all in 1 hour. So the fact that I actually can take a little more time to go through the material is a great advantage, I think, for me, hopefully for some of you that go to the 3 lectures. Today's lecture is going to be a bit historic. So I'm going to begin from how the ideas of gravitational waves came about, to the controversies over the theory itself, to the beginning of experimentation and what it took to do it up to the discovery itself. So that much I'll cover today. In tomorrow's lecture, which will be in the afternoon, it'll be a little bit more technical, not super technical, but a little bit. And there I'm going to concentrate on how we interpret the signal that I'll show you today and what technically it took to make the measurement. What are the elements that it took to make an instrument that was sensitive enough to make this measurement. And then on Wednesday, is that right? Yeah, Wednesday, I will talk about how we interpret these results, what some of the other gravitational wave signals we can look forward to seeing, starting a new science which is looking at gravitational wave astronomy, what some of the other ways of looking at gravitational waves will come about over the coming decades, and basically what the future is of this, what we think is a brand new science. So that's the plan. Today, as I say, will be quite historical, but also technical and scientific. So let me start, not with Einstein, but I'll go back to Newton. So we all learned about Newton when we were in school, all of us. And Newton probably, arguably, maybe Einstein equivalently, was the most famous physicist of all time. And his theory of gravity, which is what I'm talking about here, or what he called unified gravity, is perhaps the most successful theory of physics ever. It was eventually replaced by Einstein's, which I'll discuss in a few minutes. But in going back to the year 1687, Newton published his great works called the Principia. And in that he had, for example, is where he laid out the scientific method, something we all have learned about as the way we approach science, maybe not formally, but the way we basically approach science. And in that, he also had his universal theory of gravity. So Newton's theory of gravity came about in 1687. It described what happens if you have two masses, like described here. We all learned this in school, that the force that attracts them, the gravitational force, is proportional to the product of the two masses. It's inversely proportional to how far apart they are squared. And there's a constant in front which describes the strength of gravity. Interestingly, Newton did not address how strong G was. It was left as a letter. This worked to describe everything for more than 200 years, almost everything. Whether it's the motion of the planets or the tides that we have in the ocean, or the apple falling out of the tree, basically this described gravity. So that was Newton's contribution. It actually took 100 years before anyone could figure out how to determine what this capital G is. And that was done by Henry Cavendish 100 years later. And when he did it, he developed what's called the torsion pendulum, a bar that hangs down. If you twist it, it wants to restore itself. So on the bottom, he put a long bar, and two weights on the ends. And then he practiced by twisting it and seeing what the restoring force was, and eventually brought up two lead balls and saw how much it twisted. And with that, 100 years after Newton introduced his formula for gravity, he told us how strong it was, or what capital G was. And the answer he got, I write here, in the units we use in physics, which you can ignore for here, but I put it for completeness. It was 6.75 times 10 to the minus 11. And realizing that it took 100 years to do this, it's interesting that I put on here the best number as of today, and he almost had exactly the right answer as the first person to ever measure it after people couldn't do it for 100 years. So that was Cavendish, that was the theory, and basically for almost everything until Einstein's time. I'm trying to set the stage for what we knew and didn't know at the time Einstein came along. So basically that was even though it's a rather simple formula, that was what was known. And it was successful for everything, as I say, that anywhere which involved gravity. The next person to come along that played an important role was a French mathematician who ended up being dubbed the father of celestial mechanics, Urbain Le Verrier. And Urbain Le Verrier used the formulas of Kepler for planetary motion and Newton's laws for gravity, and together more or less explained everything about the orbits of planets. But he noticed that the planet Uranus had an orbit that didn't quite work. It didn't satisfy the equations of Newton and Kepler. That could have been thought to be maybe a breakdown of the rules of Newton, but instead he took the leap or hypothesized that there was a missing planet, and that was why you couldn't fit exactly the orbit of Uranus. So he did the calculation to determine what this planet would be, and found that there could be a planet, where it would be, how big it would be, and he even named it Neptune. And he sent a letter to an astronomer in Berlin. He was in Paris. He sent a letter to an astronomer in Berlin. He gave it 5 days to get from, at that time, to get from Paris to Berlin. He told the astronomer where to look in the sky, and he looked in the sky, and to something like 1 degree, he found the planet Neptune. So this made Le Verrier very famous, and he dubbed, as I said, the father of celestial mechanics. Well, scientists like to use the same trick more than once, often if you're successful, and this happened to Le Verrier. So he basically realized 25 years later, he did all what I told you so far in the maybe 1820s and 30s, and in the 1850s, he noticed that the planet Mercury, our planet that's closest to the sun, also didn't quite follow the laws of Newton. And of course, since he was successful before, he hypothesized that there must be another planet or bodies between Mercury and the sun. Mercury has a peculiar orbit in that it's very, very, I'll show it in a second, it's very, very long and elliptical. Anyway, Urbain Le Verrier, as he had for Neptune, named what hadn't been seen. He called it Vulcan, and hypothesized that there was something. In 1859, he wrote the paper, that there was a planet between Mercury and the sun. There were a lot of searches, and in fact, as happens often in physics, people who claimed a discovery, which was then disproven by better searches later. So people looked for Vulcan, but it was not found by the time Einstein came along. It also wasn't disproven that there might be something between Mercury and the sun. It was still an active piece of research. So laying the groundwork for Einstein when he came, there was a discrepancy, maybe significant, maybe not, for Mercury around the sun that was there considering Newton's theory, but nothing else after more than 200 years. So it makes you wonder why Einstein, who in 1905 published several papers, 1 month at a time, on different outstanding problems in physics, and basically became the hero of all physicists since that time, with all the problems he solved so quickly, and then spent 10 years developing the theory of general relativity. It's hard to believe that he did it because of this small discrepancy of Mercury around the sun, although some people have hypothesized that that's the reason. There are two kind of clear flaws, or discrepancies, or incomplete aspects of Newton's theory of gravity. The first one is that when we were all kids and we were in school, and our teacher told us that the apple is pulled by the earth when it falls off the tree, and told us that if we jump up, the earth pulls us down. Most of us probably just believed it at that level, but maybe some of you asked your teacher why the earth pulled you down. Newton didn't explain why. So Newton's theory, although he gave us a nice formula and it worked very well, didn't describe what is it that pulls two bodies together for gravity. And in fact, most attempts in the next 100 years or so to describe it try to do it by some form of electricity and magnetism. So nobody developed a new form. Einstein's theory, which I'll come to, does it by having the reason the apple falls to the earth, or the reason the earth goes around the sun, has to do with the distortion or warpage of space-time around any massive object. So the massive object, being the earth, distorts space-time around it, and other objects will be pulled to it. Anyway, after Einstein came along and even came out with the theory of general relativity, NASA kept looking for whether there was any object between Mercury and the sun. So sophisticated modern technology and satellites were used. Nothing was found, and the last time we heard about Vulcan was actually a television program. So what about Mercury around the sun? Mercury around the sun, the discrepancy that I'm talking about is that Mercury itself, going around the sun, has a very elliptical orbit, as shown here. And when it goes around, because of the positions of all the gravitational pulls of the planets, moons, and so forth, it comes back to a different place. So you can calculate how far it moves each time it goes around. That's in some units shown here, 575 arc seconds per century. And Newton's formula is not quite right, so it gives this discrepancy, which is about 10% wrong. And as I said, at the time Einstein came, that was the only discrepancy that existed in terms of measurement or anything else. So the first way that Newton's theory conceptually wasn't complete is that it didn't explain to us as school kids or later why the earth would pull us down, so why these things would work. The second failing, which Newton actually realized in his theory, is that it has, in the words that we would use as physicists, instantaneous action at a distance. That means when the apple falls, you know it immediately. That's okay for the apple, but if the sun were to burn out while you're here, it takes 7 seconds for the light to get here or for us to know that the sun had burned out. And it's not reasonable that the gravitational signal would get here immediately. So Newton's theory didn't have any time or finite speed of information travel. Instead, it's basically infinite or not addressed. So those were the two flaws that existed in Newton's theory. So even though it described everything, once we add Einstein's theory, it fixes both those problems and gets the right answer for Mercury around the sun. Einstein's theory, which I'm not going to go into any mathematical detail here, is a little more complicated looking than Newton's formula, but this is the equivalent formula from Einstein. And it basically has the feature that space and time are put together in one four-dimensional system. That's space-time. So it becomes one word in a sense. Space-time is one word. Bill Gates doesn't know that yet, so when I put it in Microsoft Word, it puts a little wavy line underneath. But it's all integrated together, and it's the complexity that makes it difficult for students of physics to learn general relativity, difficult for scientists to understand it, difficult to visualize it because it's four-dimensional with space and time, and difficult to get the right answers when you calculate things, as I'll talk about. So Einstein introduced this theory. It fixed these two problems. Much of physics moved into quantum theory, so it had some people that worked on it in physics, but not all, of course. And Einstein wrote this, as I say, in 1915, 10 years after he had written this set of incredible papers. Okay. In general, we don't accept a new theory in physics, certainly after 200 and some years, like we had in the case of, I'm going to cool down, if I can get this off. Like we had in the case of Newton. So to accept a new theory, in general, what we expect is if somebody has a new theory of physics, it's going to do more than fix some problem in an old one, and this didn't seem like a huge problem, really. It fixed also two conceptual problems, as I said, which are probably more important, and probably more the motivation for Einstein. But it needs to predict something new. So in this case, Einstein recognized that immediately, and he made a prediction. He predicted exactly how much and that light would bend if it came near any sort of massive object. That's obvious in this theory kind of pictorially, because if I have an object, this is the sun and the earth, this is a coordinate system. I can't do it in 4 dimensions. You have to look at every point on here and realize it has x, y, z, and time. And it distorts the ones near it. So each point here is distorted also in time, x, y, z, and time. Here's the Earth. And if this wasn't the Earth, clearly it was just the apple. It falls toward the lower point and would just fall like a trampoline that you put a bowling ball in the middle of. It'll roll toward it. So that's obvious. And in the case of the Earth, if it's going at some speed around, then it tries to go out by centripetal force, and it goes around on orbit. What Einstein realized, in addition to this, is that this picture here did not depend on the object being affected having any mass. In other words, the Earth creates all this, except for this little dimple here, which was caused by the Earth. It caused all this. So it doesn't matter when we talk about the fact that the Earth has mass in terms of what happens to it. It gets sucked toward the fall and potential here into this well. So if I have light and it comes near this, it will also bend. It doesn't matter whether anything has any mass. So Einstein picked up that issue and predicted that if we had light going past the sun, from some star behind the sun, the light would bend as it went around the sun, and he calculated exactly how much it would bend and proposed that the light be followed from a full eclipse of the sun. And he proposed that it be done, I think, 2 years after 1915 and 1917 in an expedition to what was becoming the Soviet Union at that time. That expedition failed for political and military reasons. But 2 years later, the British scientist, Arthur Eddington, took an expedition to the southern hemisphere and measured a full eclipse of the sun. When a star cluster went behind it and measured the bending as it went by, and it was exactly as Einstein had predicted. And that was the clinching experimental fact that made people believe general relativity, and I believe made Einstein a household name, because his name was in papers all over the world as for this dramatic thing that light had bent, and he had predicted how much in going around the sun. And Arthur Eddington became Sir Arthur Eddington. So now we have a new theory. It fixed the small problem that existed after 200 and some years with Newton. It predicted something new, as I said, and basically had some grounding. Einstein recognized over the next year that yet there was another effect, or he thought there might be another effect. And that was what the rest of these lectures is about, and that's gravitational waves. So in 1916, only months after he had come out with the theory of general relativity, he wrote a paper, which I show the front page here, which predicts that there will be gravitational waves. That paper isn't a very good paper from the standpoint that it has at least one mistake of a factor of 2, and it doesn't develop gravitational waves from fundamental principles of general relativity. Instead, it was pure Einstein. He looked at the equations in setting it up a certain way and recognized that the equations had a similarity, with different letters, of course, to the equations of electricity and magnetism that we all know, Maxwell's equations of electricity and magnetism. And then he made the leap. If the equations look the same, then there must, as there is in electricity and magnetism, where we have electricity, we all know that from the lights and everything, magnetism, which we all know, and we have electromagnetic waves, all kinds, radio waves, microwaves, and so forth. He made the leap that if the equations have the same form, there must be also gravitational waves. So he didn't develop it from first principles. The paper was not well written. He realized that. He wrote a second version of the paper 2 years later, in 1918, and that version of the paper fixed the factor of 2. Of course, being Einstein, he never recognized that there was a mistake in the first one. He just went on and did it right in the second one. But it also set a guidance for somebody like me, an experimentalist, because what he did was talk about what would be the source of making gravitational waves. In electromagnetic waves, we all know that electromagnetic waves were discovered in the late 1800s after we had equivalently a theory of electricity and magnetism written down by Maxwell. And those equations basically have electromagnetic waves, and they were seen for the first time by a physicist named Hertz, who took what you have in electricity and magnetism, that is a dipole, 2 charges that oscillate and make waves, which are electromagnetic waves. So he made a source. He went in the next room and made a receiver, a radio receiver, and detected the waves. And then he moved it forward and backward and saw that it was wave-like. And that was the discovery of electromagnetic waves. So likewise, we have now the same kind of form of equations, and Einstein hypothesized there must be gravitational waves, just like there are electromagnetic waves. I'm going backwards somehow. Oh, maybe I just have extra slides. Okay. So before I get into gravitational waves, and before I leave general relativity itself, I want to point out that we all may think of that as a very abstract subject, but almost all of us use it almost every day. And without it, we wouldn't be able to do what we do, and that is the GPS system. So the GPS system, which is on your, in your car, on your iPhone, and so forth and so on, basically is dependent on 24 satellites that circle the Earth. And the 24 satellites are at about going about 14,000 kilometers an hour. That's the speed of the satellites. There's 24 of them circling the Earth. And if they're going at 14,000 kilometers an hour, that's fast enough to require Einstein's special theory of relativity, E equals mc squared, the special theory of relativity. And there's a famous expression that we all learn when we learn special relativity, that moving clocks tick more slowly. That's how we remember which way it happens. And in this case, that's what happens. In the satellites, they tick more slowly, and you have to make a correction. That correction is actually 7 microseconds per day. So in the satellites themselves, that correction is made, 7 microseconds per day. But it's not the end of the story. The satellites are also well above the Earth. They're high enough so that the gravitational field at the satellites themselves is about a quarter what it is on the Earth. Therefore, the warpage of space-time, all what we've been talking about, is less. And in this case, the clocks actually tick quicker, faster. And that correction is 45 microseconds per day. So the total correction is the sum of the two, and the GPS correction is 38 microseconds per day. That correction is actually made in the satellites themselves. It's kind of amazing, but the satellites that were developed by the US military, the military, of course, didn't understand general relativity, but they got convinced to make the correction when they put up the GPS system, which was originally done for those purposes. Anyway, so I've just done numbers here. How much does it really matter, this little correction? It does matter. It turns out that if I put the numbers in and I asked for the accuracy to stay on the road, that is, the accuracy to stay on the road, if it drifts more than 30 nanoseconds, I would go off a road that's 10 meters wide. So I can put the numbers in, which I didn't bother to do for you here, of how much happens in a day, how long does it take if I drift that much. It's about 2 minutes. So your GPS system would keep you on the road for about 2 minutes if we didn't use general relativity. So if you don't come home with anything else today, realize that general relativity does matter for all of us. Okay. Einstein and essentially nobody else visited the problem of the possibility of gravitational waves for 20 years, almost 20 years, 18 years. Einstein, most physicists were working in quantum theory. Einstein was trying to do more on unification. He didn't come back to this problem until the 1930s, after he had immigrated from Berlin to Princeton University. And when he was at Princeton University, his associate or assistant was Nathan Rosen, and the two of them re-looked at the problem of gravitational waves starting in 1934 or 1935 to try to develop it out of the equations of general relativity rather than the hand waving that the equations are similar. So it was an unsolved problem to do that. They worked on that for some time and basically got a result and wrote a paper which is entitled, "Do Gravitational Waves Exist?" Funny title for a paper written by somebody who said they did exist 18 years before. So you can imagine that the content of this paper maybe wasn't what he originally intended to do, which is to develop gravitational waves from first principles. And the problem was that that we often have in general relativity, as I kind of alluded to earlier, that because of having 3 space dimensions and time altogether, it's difficult to do the calculations. You have to be very careful how you set up general relativity problems. If you set them up wrong, you get often infinities and so forth, which we call coordinate singularities. And that's what happened in this case to Einstein and Rosen, but they didn't quite recognize it. They got more afraid that maybe gravitational waves don't exist. They wrote a paper. They submitted it to PhysRev, I don't know whether it was called PhysRev or PhysRev Letters at that time in the US, which was the most prestigious American journal. And the editor of PhysRev at that time was named John Tate, a rather young man. You can see he's kind of young in this picture. And he had the problem of how to deal with this paper. You have to realize, going back to the 1930s, that now when we submit papers for publication, it's just part of the system that we have what we call anonymous peer review. Papers are sent out to anonymous reviewers. Depending on what those reviews say, the editor decides to publish it. In the 1930s, I don't know whether Einstein experienced any refereeing system in Germany before he came to the US, but I do know that in the US, probably not, I assume, but I don't know. But in the US, they were just initiating for the first time peer review into the physical review, and John Tate had that responsibility. Clearly, it's anonymous peer review. You generally don't have the ability then to look at what happened, but now many years have passed. It turns out that I served as president of the American Physical Society that runs the physical review journals, and you can actually go now and look at the old records. So I'll show you the old records. So this was sent out. So this was sent out for review. This is the man that reviewed it. His name was Howard Percy Robertson, who also happened to be at Princeton University at that time, but wasn't really a close associate of Einstein's. And he was on sabbatical at my university, Caltech, in Pasadena, California. So he got the paper to review while he was at Caltech in Pasadena, California. And down at the bottom here in handwriting, because then we didn't have computers and all that kind of stuff, is the logbook for physical review letters showing what happened to the papers that came in. So the first paper on this page, this is 1936, you can see. The first paper on the page was rejected just by the editor himself. So he had the right to just reject a paper or accept a paper, as one down here was just accepted, no referee. And in between, there's this paper, which was sent out to review to this man, Robertson, and it came back about a month later. So they sent it to review to Robertson. Robertson, who, as I say, was a general relativist, actually looked at the problem and understood why they were getting the infinities and reset up the problem in the way they did, but in what we call cylindrical coordinates. And so he wrote back a letter to Tate, the editor from PhysRev, saying what was wrong with the paper, and gave Tate the problem then of dealing with Einstein. Tate wrote a letter to Einstein, which basically said, I quote from it, that he would be glad to have Einstein's reaction to the referee comments and criticisms. Pretty mild, I would say. Most of us had turned in a paper that had that, we would get a rejection or something worse, I don't know. Anyway, so that's basically where it stood. Tate wrote a very mild letter back to Einstein. I didn't bother to copy that, but basically telling him this. And Einstein got the review and basically did this. And this is a copy of his letter back to Physical Review. So he wrote a letter back to Physical Review, and he said, we, Mr. Rosen and I, have sent you our manuscript for publication and had not authorized you to show it to specialists before it is printed. I see no reason to address the, in any case, erroneous comments of the anonymous expert. On the basis of this incident, I prefer to publish the paper elsewhere. It's true that Einstein never published in Physical Review again for the rest of his life. He sent this paper to the Franklin Institute. People have probably heard the Franklin Institute was named after Benjamin Franklin. It's in Philadelphia. And at that time, it had a journal. It has no journal now. They must have been delighted. They took the paper, they accepted it. They didn't have peer review, apparently, and they were going to publish it. In the meantime, Robertson went back to Princeton. His sabbatical at Caltech was over. He went back to Princeton, and he met up with Einstein's new assistant. Rosen had gone back to Europe. His assistant was another well-known man, Infeld, who was well-known, and he didn't see Einstein himself. And in fact, what I'll tell you next is what people conjecture. Everything I've told you till now is actually documented. And that is that he discussed it with Tate. He showed Tate how, if you set it up in cylindrical coordinates, these infinities go away. And Tate then, Infeld then went to Einstein. This part is conjecture, and Einstein said he already knew, had found the problem, so who knows. They then resubmitted the paper. It took a long time to publish in those days, luckily for Einstein and Rosen, because you had to set up all the type, you had to get a copy editor, and then they redid it, so it took months before a paper would come out. In that interim is when all this happened, and by the time the paper came out, it actually took care of this problem and had a new title. The title is rather vague. It just says, On Gravitational Waves. And the first sentence, I'll read to you if you're too far back to see, the rigorous solution for cylindrical gravitational waves is given. So you remember the cylindrical coordinates, and it goes on. So it's not a real proof from first principles, but it's the closest we had. The rest of the story on gravitational waves, nothing happened for another almost 20 years. In general, I think there was skepticism in the theoretical community. Outside of the general relativists, nobody paid any attention. And it finally came to a point in the 1950s where a meeting was called in Chapel Hill, North Carolina. This meeting was called by two well-known general relativists, Bryce and Cecil DeWitt, and 44 of the theorists in general relativity that were somewhere close to this problem. And they came together for several days in North Carolina, as well as one experimentalist, who I'll show you later, started on the first experiments. So at that meeting, if you wanted a date of time, I'll tell you what happened at that meeting. The problem of whether there are gravitational waves in terms of the theoretical community was resolved. It was resolved because of at least because of two key presentations there. One by a theorist named Pirani, a British theorist, who in a very elegant way developed gravitational waves out of the theory of general relativity. So he did what Einstein hadn't done 20 years before, or 40 years before. And in addition, at that meeting was Dick Feynman. And Dick Feynman always looks a little differently at the problems. And in this case, he said, well, if there's gravitational waves, and they're real, they have to somehow be able to transfer energy. Otherwise, it's just a fictional thing. And so how might they transfer energy? So he made a kind of Gedanken experiment, or a fake experiment, which is shown here. He called it the sticky bead argument, Feynman did. And the argument is the following, that if I have a bar like this, and put a couple rings around it, and then a gravitational wave comes through, it has, as I'll show you later, it has the feature that it expands and contracts the bar, which puts some frictional pressure on these. These will move back and forth, and due to the friction, and the friction is heat, and that's energy. So that picture was both convincing in terms of a physical argument that gravitational waves weren't just mathematical, as Pirani had showed, but also physical. And this method is essentially the first method that was tried, as I'll show you next, to detect gravitational waves. So this was the argument. And everything I've said to get to this was, me being an experimentalist, was to make the excuse that it really didn't take us 100 years experimentally to detect gravitational waves. The theorists horsed around for 40 years first, so it only took us 60 to measure gravitational waves. The first sentence of our paper says that it took us 100 years. It doesn't quite say that. It says that Einstein predicted it in 1916 and then 100 years later, and that Schwarzschild had also predicted black holes, which I'll talk about in a while, the same year, and 100 years later we saw them. But 40 years of that I blame on the theorists, then we took a long time. Okay, so next, let's look at gravitational waves and what their effect is and how you can go about detecting them. And remember what I talked about in the sticky bead argument, because it's the first technique that was tried. So the first statement is that gravitational waves are not like electromagnetic waves. Electromagnetic waves, when they go through space, are carried by photons, are attributed to photons through quantum mechanics, so we have a carrier. In the case of gravitational waves, at least classical gravitational waves from general relativity, there's no carrier. They're just basically distortions or ripples in space-time itself. A little bit like throwing a pebble in a clear pond, and it goes to the bottom, and the little ripples that go off are just part of the water itself taking a different form. So there isn't some object carrying it. So that's the first qualitative feature. It's not like electromagnetic waves in that sense. Secondly, the amplitude that is measurable by the kind of technique that I'll talk about, and I'll come back to that, is a little term h, which is the term out of general relativity. It's the strain or the amount of distortion of space-time that you get. And it's a very tiny number, 10 to the minus 21. I'll show you that on the data in a little bit. But the number that is kind of conceivable and that you need to be able to do to be able to see it is a very tiny number, 10 to the minus 21. What does it do? It basically distorts space and time, of course, but I'll work with space for the purpose of this. And that is that if I have a bar that's this long, then if I actually ask what happens to it, it'll change by 10 to the minus 21 times its length. And that's this. H is delta L, the change in length, is 10 to the minus 21, this number, times L. And a way to think about it, I show here. If I have a ring, and on the ring, I put free masses. These are free to move. And the radius is L. Then the distortion will be, this will become slightly elliptical. And the distance is just, I didn't write that well, but it's 10 to the minus delta L, the distance here, is 10 to the minus 21 that it changed. Times, if this was a meter wide, a meter, so I'd have to measure 10 to the minus 21 meters. It's a meter's this big, I have to measure 10 to the minus 21 meters. We make that easier in the case of the experiment that I'll report in a few minutes by making it not a meter long, but kilometers long. So this number, 10 to the minus 21, becomes more like 10 to the minus 18. And that's the size we have to measure. So Einstein's theory of gravity basically says that if there's sources that have this quadrupole moment that I described, then two stars going around each other would have that, or a barbell going around each other would have that, would have the quadrupole moment, then it basically will emit gravitational waves that'll propagate away at the speed of light, and basically that's what we'll try to measure. So how should we do it as experimentalists? Clearly, in experimental physics, the most reliable thing you can do if you're trying to do an experiment is to make sure you control all the variables. If you don't control all the variables, then it's much harder. So what you'd like to do is just what Hertz did. You remember Hertz made a little source, went in the next room and detected it. He could fool around and change the source if he wanted. He could change the detector, and so forth. We don't have that luxury, as I'll show you. Imagine that I made an experiment to do this. To make the quadrupole moment, you make something like a barbell like this and rotate it around. And if you do that, you get basically an effect that if I put in these numbers here, that is, this is 1 meter across, these are, say, a kilogram, that I rotated 1,000 times a second, and then I better get out of the room because it's pretty wild. So I've exaggerated them all. And I go into the next room, which is only 300 meters away. I'm trying to exaggerate the effect to make it as big as I can. That's not far enough to see the wave-like motion. You have to be 10 times further. Then how much do you get here? Whoops. You get 10 to the minus 35 for this effect. And what I'll show you by what we do from black holes is we're capable of measuring an effect that's 10 to the minus 21. So even though the effect that we're measuring is incredibly small, if we actually tried to do what Hertz did, it would have to be 14 orders of magnitude smaller yet, which clearly we can't do. So we have to rely on nature to make the source instead of make our own source. Fortunately, nature made a source that's strong enough, and fortunately, that source is also very interesting. So we were lucky in that sense. And this is the source, which I'll come to. That is, it looks like the barbell. It's two black holes that are going around each other. As they go around each other, they, by Einstein's equations, are accelerating. They radiate by going around in the circle. They radiate away energy. That's radiation is in the form of gravitational waves, which we'll detect in a while, as I'll show you. And we basically can try to detect that. Okay, before we get to our detection, let me start with the first experimental attempt. This is the 1960s, and this man, Joe Weber, was the first to try. He was the one experimentalist who was at this meeting in Chapel Hill, North Carolina. And he made the first detector, and the first detector will look a little like Feynman's sticky bead argument. This is the bar. He made a bar that was 1 or 2 meters long, big bar of very, very pure aluminum. And around the waist of it, here, he put very sensitive detectors. These are PZT detectors, they're called, that can measure any strain if the bar changes its shape a little bit. So if a gravitational wave comes through this, then the bar changes because the space gets warped, space a little bit, exerts a little bit of pressure on this, picks up the signal, and that's the gravitational waves. That was done in the 1960s, as I said, with a very pure bar of aluminum. Those first searches were really very brilliant, that he developed the technology, the electronics, and so forth. Unfortunately, he thought he made a detection when he didn't. So in 1969, he was the first to claim that he saw gravitational waves. That is the picture from Physical Review Letters that was published in 1969, where he saw what he thought was a signal from gravitational waves in 2 detectors, one at the Argonne Laboratory near Chicago, and one at Maryland, University of Maryland, where he was a professor. And he published this in 1969, but unfortunately, it wasn't correct, and several experiments were done that were at least 10 or 100 times better than his that didn't see such an effect. So he was incredibly important for experimentalists in starting this field. He even did several things that are basically built into what we do in LIGO, which I'll list here just to give him credit. He did sensitivity calculations for what bothers you in the end, the various sources of noise. We do the same thing. He did a coincidence, which he did between 2 different detectors distant from each other in order to try to reduce any background problems that you might have. We do the same. He finally did a way to evaluate what the backgrounds would be by looking at these when they're not in time instead of in time, to see how many times you get deviations that look like they're in time, but they can't be. And we do the same thing. So he started the field. He was a very clever experimentalist. Unfortunately, he claimed detections that weren't correct, but we use some ideas that he did as part of what we do. Now, before I get to our experiment, I want to go through one other thing, and that is that another very important experiment was done by Hulse and Taylor. This is Hulse, and this is Taylor, in that they saw indirectly very strong evidence for gravitational waves in an experiment done over a period of over 20 years, looking at pulsar signals with a radio telescope. They looked at a particular pulsar system called PSR 1913 plus 16 with a radio telescope. So what is a pulsar, and what was the experiment? We have in our own galaxy neutron stars, which are products of the death of a star. If the star is not so big that it might make a black hole, it makes a neutron star. We don't know in detail what a neutron star's detail looks like, but the best models we have of what they look like I described here. They're about 1.5 times as massive as our sun. They have a solid crust on the outside that's about 1 kilometer or 2 kilometers thick. The whole thing isn't much bigger than the size of a medium-sized city, about 20 kilometers across. And the inside is made up of a lot of neutrons and other particles that are supposed to be heavy and very dense liquid. So that's a neutron star. It then has made and been detected as signals in radio pulsars because they tend to rotate. They have currents in them. The currents make signals that come out of the ends. So if it's rotating around, radio signals come out of the ends of a radio pulsar, and you see periodic signals. It works a little bit like a lighthouse, that when it points at you, you see it. When it isn't, it's dark, and every time it comes around, and that gives a signal. And so pulsars are watched by seeing this. They were studying a particular pulsar system, the one that I said, and they were going, this is Hulson-Taylor, they were going to study it in great precision. They weren't looking for gravitational waves. And in order to see how well it all fit together, they were studying a system called PSR 1913 plus 16. And it consisted of this object going around and around 17 times a second. So they have a signal that's going like a lighthouse 17 times a second. They're detecting it with a radio telescope. And with that radio telescope, they were longitudinally measuring it over some period of time. And they noticed that they weren't searching for it. They noticed that there was an 8-hour modulation on the signal, that it changed kind of every 8 hours. After a while, they realized that meant that there was a second object, that this wasn't a single pulsar, but like the Earth and the Moon. There was another pulsar that was going around the first one, and they inferred that the period of that was about 8 hours. So the picture they had was this picture here. They measured then the period of this 8-hour cycle by inferring how much this got modulated over a period of about 20 years. They first were measuring everything very accurately, so they measured that one object was 1.4 times the mass of the sun, the other one was 1.36, that the orbit was elliptical with an ellipticity of 0.617, and they were separated from each other by about 1 million miles. The predictions from general relativity, once you have the two, are straightforward to calculate because we have the two going around each other, and there's a certain amount of energy then given away because of the accelerations to general relativity. You can calculate it. And after it goes around each orbit, it loses a little bit of energy and slowly spirals in, so that this loses basically 3 millimeters per orbit, and the rate, that changes the rate or the time it takes this to go around, so the period goes down just a little bit. And they measured it here. This is after they were awarded for this, but so this is the beginning, the time, this is seconds, and the years from 1975 to 2000, and you can see the line, the dots along here. The dots are their measurements, which they'd make how long it took to go around, what the period was very accurately. The dots couldn't be drawn small enough, actually. The line, you'll see, goes right through them. And in contrast to typical physics experiments, that line is not a fit to the data, but a calculation using the parameters of the system from general relativity. And it goes right through the data. So this was an indirect proof that there's a system that's losing energy, and that energy presumably is going off in the form of gravitational waves. Okay, so now comes the new scheme and what I'll talk about the rest of the time, and that is using interferometry. So the idea here is that light comes, you divide it in two perpendicular directions. It goes down a path which we've made kilometers long, hits a mirror and comes back. If the two arms are the same length, they'll come back at exactly the same time. They'll cancel each other, and nothing will be detected in the detector. But if one of the arms gets a little bit longer because of distortion of space-time, then they will add to each other instead of subtract, and you measure a signal here. In simple-minded terms, that's how interferometry works, and it's what we use in LIGO, our detector. It basically is that simple. In general, in experimental physics, it's really difficult to measure something absolutely, like how big is a meter stick or how much is a kilogram. And we have big institutions that work to make In the US, it's the National Bureau of Standards, and there's a big institution similarly in France. And so having the standards for everything we have is a big deal, and it's tough to do. It's easier often to measure something that should be the same or barely is different from each other, to measure a difference. In our case, this is almost ideal because we measure a difference of something that should be the same. The two arms are the same, the light comes back and cancels. If one of them gets a little longer, then we can detect it. So that's the scheme of interferometry that I'm showing it a couple times a second here. What happens? It gets longer in one direction, then shorter in the other direction, then goes the other way, and that, I've lost my formulas. Okay, I'll tell you in words. So, there was a piece of that slide missing, and I'll tell you in words. Basically, there are two challenges experimentally, most of which I'll talk about tomorrow, but I was just going to tell you the numbers today. In order to be able to measure accurately enough to see the kind of effect that we see, this little 10 to the minus 21 that I talked about, you have to be able to do two things. One is do the interferometry where I showed wavelengths. You have to be able to do it to one part, the wavelength in one part in 10 to the 12th. This is called splitting a fringe, if anybody ever used an interferometer. People who use an interferometer in a freshman or sophomore laboratory maybe see fringes and can split a fringe to one part in 10 or 100. Very good interferometry might do it a factor of 1,000 better than that. But we have to do it to one part in 10 to the 12th. So much of what we've done over 20 years is learn how to do interferometry itself with unprecedented accuracy, and there's an incredible number of very clever experimental techniques and tricks that are used to do that. The second problem is that we live here on Earth, and we're trying to detect gravitational waves on the Earth, but the Earth shakes a lot. And so we have to isolate ourselves from the Earth itself. And again, the number is similar. We have to isolate ourselves from the Earth. We don't want the isolation. We have to suspend this thing somehow and make it free from the Earth so that any shaking of the Earth is reduced by a factor of 10 to the 12th. Those are the two experimental challenges, which I'll talk about tomorrow. But let me go back to what we detected first, so I end this with a piece of physics. 1.3 billion years ago, there were two black holes shown in this picture here. And those two black holes that are shown in the picture here are drawn by a computer rendition of our data, not by an animator. What's shown is the universe and the two black holes. But before I show them what they do, let me remind you what a black hole is, at least so we can all understand it in simple-minded terms. It's, of course, a very difficult concept mathematically. I won't deal with that. Let me do it physically. It's a region of space created by matter that's so dense that nothing can escape from that matter, even light. Light, you remember, gets curved by general relativity, so nothing can get out of it. Then it's defined as a black hole. A region of space like that is created when a star burns up all its fuel and collapses. Not our sun, because it's too small, it can't make enough density, but we think that stars larger than about 3 times the mass of our sun can give this very big density that we call a black hole. So that's what these black holes are. The ones that I'll show you that we detect are about 30 times the mass of our sun. This is from our data. The two black holes going around each other. As they go around each other, they attract each other. And eventually, they're, in the meantime, affecting everything around them, as you can see in the galaxies and so forth. Eventually, they radiate enough so that they merge together, as you'll see here, and then they'll settle down with some shaking a little bit. And all of that has a lot of physics in it, but that's the process of what happens, and then you end up with one bigger black hole. The bigger black hole is not the sum of the masses of the smaller black holes, but the sum of those masses plus the energy that went away in the form of a radiation, which is gravitational waves. And this is now showing the gravitational waves. So as they're coming in, they're emitting gravitational waves. Those gravitational waves that we detected started 1.3 billion years ago. They then were coming toward us on the Earth. I show them getting to the Earth, but in this picture I exaggerate a little bit how much it affects the Earth, but it's going to distort space-time itself, so it distorts the Earth. But as I said, the Earth itself is a little hard to deal with, so we have to put an instrument instead to see that distortion. That instrument's called LIGO, which I'll talk about in more detail tomorrow, but it's the instrument that does these two things. It does interferometry at a level of 10 to the minus 12 of what the size of the wavelength of the light that's in it, and is isolated from the Earth by a factor of 10 to the 12th. Okay, I lost a picture here too. This picture showed a picture of the Earth, and the first thing that happened is that this gravitational wave that we detected, that was the first ever detection of a gravitational wave, was on September 14th, 2015. And in this picture, you'd see that we know that it came up through the southern hemisphere, but not very accurately. And there's a picture that shows that. I'll show it in a future slide. This is the first detection. So in Livingston, Louisiana, on September 14th at 5 o'clock in the morning, this trace was seen. So what are we looking at? This is time going this way. This is the size of the signal this way. And if you can't read it, this is the units I was talking about before, 10 to the minus 21. So 10 to the minus 21 is from here to here. And you'll see this has a shape that does this. What it's doing is, to you, might look just like wiggles, but it's a particular kind of wiggles that we expect. That is, they get bigger as time goes along, and they get narrower as time goes along. And that is a shape that we call a chirp signal. It goes whoop, and I'll try to show that. 7 milliseconds later, in a second piece of apparatus that we have 2/3 of the way across the US, one in Louisiana, the second one in the state of Washington. State of Washington, we see this. And even to your eye, you can see that they look a lot alike. And so this is the raw data. It's many times in physics, we spend a lot of time on computers doing all kinds of things before you ever see the data. And then we show you the data after we've massaged it. This had nothing done to it. It's what we saw right away from the online data. So that's the signal. And in here you can hear this chirp signal. So what happens as it comes, what's plotted this way is frequency, and this is time. And as they merge together, they're going faster and faster. So it has a shape that goes like this, which is the so-called chirp shape, and the detailed registration of it is shown here in the two labs. So that's what we detected. In terms of what we think it is then, and I'll show you how that works in a minute, this is what you expect from general relativity for such a system. That is, you start with two objects, they're going around each other, like the Earth around the Moon. These are two more or less the same size, and it's doing this. As they get closer together, it gets narrower and somewhat taller. Then they merge together, that's here, and eventually make a little ring down. What's shown down here, this is a fit to our data, by the way. But what's shown down, and I'll show how that works in a minute, but what's shown down here is two things. One is how fast these are going. They're going, starting at about 1/3 the velocity of light, up to about here, 6/10 the velocity of light. So we have these two objects that are going around each other at a good fraction of the speed of light, radiating away gravitational radiation. The distance they're apart is about, and the scale here is in units that you don't know, but it's about 100 kilometers apart. So what I've shown here, and it's where I'm going to end, I think, is those same two signals But maybe you can see it, or maybe you can't. There's a little white line that goes through them. That's the fit to general relativity. So we got this, and immediately one can see how well, without doing anything, it fits the theory of general relativity for two massive black holes that are in the distant universe that are about 30 solar masses each. And that's the end of what I'll show today. What I'll show in the next lectures, in addition to how and why it's possible to make a detector that can see this, more detail about what we can learn from this shape and how well we know the shape, what parameters and what we can tell about the system itself that we detected, and other systems that we can detect in the future. So with that, I'll end for today. Thank you.
Okay, thank you so much, Barry, for a really clear and very exciting lecture. I'm very curious to hear what's coming tomorrow and on Wednesday, but I'm sure there are many questions, and so now we are ready to have you interact with the audience. Just raise your hand and we'll come to you, microphone. Okay.
Just to begin, there was a dispute between Newton and Leibniz about gravitation, and if I remember well, Leibniz was skeptical about gravitation, but I have forgotten his argument. Could you tell us the argument of Leibniz against Newton?
No, I'm not really an expert either, so somebody else probably knows better than I. Sorry.
Okay, there's a question over there, so I'll get some exercise. Thought we might have a second microphone. If somebody knows where it is, please let me know.
Just a very naive question. How often do appear these gravitational waves? And how you can be sure that, I mean, I would expect to see many waves coming from many different places in the universe. How can you can single out one specific phenomenon?
Okay, so this question I can answer.
Thank you. Thank you.
Yeah, we're trying to detect something that's fairly rare, and we have to be able to make a detector that can see out far enough so that some of these events can happen. This particular event was about 5% of the way to the edge of the universe, which is the distance at the time we did this as far as we could look. So what we're limited by is the fact that we can't see very far yet, and so it's rare for these to happen. Since that time, we've improved the distance maybe a factor of 2. So we see maybe 1/10 of the way out to the edge of the universe. And we've seen quite a few more. How many are there? You can take the fact that since we've done this one, we've seen somewhere between 5 and 10. How far out we look in the universe. Assuming that they're uniformly distributed, which we don't know, through the universe, we can calculate how many there are. But what limits us is really how far out we can see. This little sensitivity that I used, that I said we were sensitive to some level, is in the words of a experimental physicist, is an amplitude. We measure an amplitude. And that means that as the gravitational wave source is twice as far away, it'll give half as big a signal, not a quarter as big. You don't have to square it. So as we improve our detector by a factor of 2, we see a factor of 2 further out, or 8 times the volume, or 8 times the rate. And so we have numbers in the literature now for what the rate is of these black holes. They're not well defined because we only have a handful of examples so far, but it's basically that. You said there's a lot of them going around. We're just not, you're right, but we're just not sensitive enough to see them. We're barely able to see far enough to see any at this stage.
Okay, are there further questions? This is the great location for the next question.
How much is the amplitude of the gravitational wave if we are very close to the event?
Well, as I say, the amplitude of the gravitational wave itself is a number that I gave, which was that 10 to the minus 21. Then you have to measure what effect there is on a length over a length to see what the effect will be. It varies linearly with the distance. So if I showed you at basically 1 gigaparsec how big the signal is, 10 to the minus 21. If we had a signal that was a half of a megaparsec, it'll be twice as big. If it was a quarter of a megaparsec, it'll be 4 times as big. So it varies linearly with the distance.
What are the prospects of refining these instruments in such a way that one can open a new window to the universe and detect even, I mean, this is an extremely violent event, 2 black holes colliding. What are the chances of, in the near future, let's say, so that we can also observe less violent gravitational events?
So I'm being asked what my next 2 lectures are, which I'll do 2 things. One is I'll project and say why, how this window will crack open over the coming decade and beyond, and what other kinds of physics sources will become available because of that. And that I'll talk about. I think what I'll say is the following today, that this has been a hard, long task to do this experimentally, but we aren't limited by nature. So we haven't run into the problem that we won't know how to make better detectors. Not that it's easy, but there's nothing fundamental in nature that's stopping us right now. It's our ability experimentally to have a quiet enough environment, to make a good enough isolation from the ground, and so forth and so on. We know how to do better, and I'll just name a few things, which I'll talk about a little bit in the next days. One is that we're limited for one reason, because we work at room temperature. Many experiments are much better because they lower the temperature, and will lower the temperature in the future. That's an obvious way. It's not easy because we have to make an interferometer like this, lower the temperature without shaking anything, and so forth and so on. But basically, that's one scheme. We can have a more powerful laser. We're not anywhere near the limit of what people can use for lasers. We've concentrated mostly on the quality of the laser, not how much power we can really develop. And there's many other ways this will improve. So I think it's going to be slow, because it's always slow to make big, expensive things. But I think we can look forward to generations of our kind of continual upgrading and improvements. And hopefully, we've already seen a second kind of source, which I'll describe in another lecture, which has to do with neutron stars instead of black holes. And I think as time progresses, we'll see many more kinds of sources of gravitational waves.
Okay, I'll allow, let's say, at least one more question. Okay. If there's no question right now, I'm sure. Ah, there is one. Yeah. Okay. Very good.
So, how long did it take you to realize that you have had detected the gravitational wave? From your raw signal in your detector, how long did it take you? Like minutes or hours? Was there a nice alarm or?
We have the feature that because we're looking for signals from astronomical events, not this one, but astronomical events in general, that might also be seen by optical or electromagnetic radiation, some sort of telescopes, that we have basically what we call an online analysis, an online trigger. If something becomes a strong enough candidate, we alert the astronomical community. Our own analysis to do it in detail might take longer. We do that regularly, and then we say, oops, a few days later when we figure out that it wasn't real. So this fit that category. We immediately had an alert that it looked like it could be a gravitational wave. It isn't the first time. And as I said, it happened at 4:50 in the morning in Louisiana, which was 3 o'clock in the morning in California, and almost noon in Europe. So the first person in LIGO that actually identified this as a possible event was not at the 2 laboratories that we have, but at the Max Planck Society in Hanover, where he saw the data. It was an Italian postdoc, and he saw the data and made a lot of emails and telephone calls and so forth. By the time I woke up in California 3 hours later, there was a long string of email. And that isn't the first time there is an alert and there's some email, but this was longer and kept looking better instead of worse as you read through them. I would say then that's the scientific story at the beginning, that we knew it was different than anything we'd ever seen, and we had to check it. Some of my colleagues, I believe, had a eureka moment at that point. I had a closer to a panic, I think. And that is kind of 2 questions. One is, this was, as I mentioned before, we're continually improving the apparatus, and it had been really redone. And this was the very early running on an apparatus that we hadn't had that long. We had tested it, but not in detail. So one question is, how are we fooling ourselves? Meaning, how is this new apparatus making us think we see something that we're not thinking, and it makes, signals like this somehow on its own? That we knew exactly how to test that, of course, but it took 1 month. And the second panic, if you want, is that data had traveled all the way from Louisiana to Caltech to Hanover. How do we know that some devious graduate student or somebody else hadn't gotten into the data and put something in there? And so we had to trace these signals back with work back to the origin and the detectors themselves, because as we assemble that little curve that you saw, we leave data in the apparatus itself and at the labs themselves before we bring it together. And that took about a month. So it was about a month later that I think all of us were convinced that we saw gravitational waves. And we wrote a paper and so forth and so on. That should convince me, and thought I was totally convinced. We saw our second example of gravitational waves 3 months later on Boxing Day in December. And for me personally, I had a sigh of relief. So, you can ask when you get, as a human, convinced. And of course, we've seen many since then.
Okay, one very last question.
I wonder, if you double the laser frequency, could you increase the sensitivity, provided that a laser would exist which has twice the frequency?
So the question is, if we increase the laser frequency, could we be more sensitive? Actually, in principle, going to shorter wavelength would be a little better than where we are, but we're more limited by how well we can make a laser, stabilize it, make it run, and so forth. So we work in the infrared. We debated a lot whether to work in the green, but we could make a better laser and more stable laser that more than balanced the gain that we would have. So in principle, you're right. In practice, for a real laser, we picked a neodymium YAG laser, one we could commercialize and one that we understood very well, and one that we could make very stable. And that was more important than the shorter wavelength.
Okay, there will be plenty of opportunities to ask questions tomorrow after the second lecture at 5:15 and then on Wednesday, but I'm sure you'll join me in thanking Barish for an absolutely superb first lecture.